and we'll go from current slide. Okay. First, any questions for anything so far? And again, I wish I had gotten the test ready by now, and you could have worked on it some this weekend, but been kind of crazy trying to get those evaluations finished, because I got all my full-time and part-time instructors. So we're continuing with applications of integration, and 7.5 is the work section. Okay? Now, the first objective, really easy. You've already done it, I bet. Work done by a constant force. Okay? If you remember the simple physics formula, work is a force times the displacement. If it's a constant force, multiply that by the displacement. Catch is, it has to be in the same direction of the force, or the displacement force in the same direction. So you may have to do a component. Okay. But the second part, where the calculus comes in, is work done by a variable force. Now it's an integral. Okay, not just a multiplication. So let's first look at work done by a constant force. In general, work is done by force when it moves an object. Okay? Usually in my physical science or physics classes, when I get to this point, I give the dumb story, but true, of digging out our patio in our backyard. Okay? When we moved into the new house we were looking at, I told my wife, I said, you know, we got a problem here. Some previous owner had built an addition in the back and dug into the hillside, so the hill went right down and had really short, squatty windows, you know, so a lot of the inside was what I said. You got all this hydraulic pressure coming onto the house when it rains and stuff, and sure it's okay now, but over time. And the second thing is, it looked like the soil went right up to wood. And in the southeast, that's not a good idea because of termites. So you don't have wood-to-ground contact. So I said, if we do get this house, and we were planning to, I said, I'm going to have to do some moving the soil around in the back and divert water and stuff like this. She said, good, I wanted a patio anyway. A lot bigger project than I had in mind. So that summer, it was my first summer teaching here when at Western State Technical College, and I was taught part-time 5-week mini-term class, 2 classes. The first 5 weeks, and had the second 5 weeks free. So I was only here 2 or 3 days, 2 days a week, I think it was. The first 5 weeks, not here at all the second. So that's when that was the digging time. Well, if you dig much in the Birmingham area, you're usually going to hit rock, okay? And I did. I mean, it was more like a boulder. I mean, I hit several rocks, and those would be a pain in the neck to dig them out together. But I had this thing, and it had to have been about that tall, and about this big around, not in regular dimensions. And I was digging on that, and I was prying on that, and cranking and doing all sorts of things, sweating like a dog. Was I doing any work? Tell me that, and I will hit you. No, you're not doing any work. You know, in physics, you're not doing work unless it moves the object. Okay, so it's a force times the displacement. So the definition is work done by a constant force. If an object is moved the distance d in the direction of an applied constant force F, then the work done is force times displacement. Okay, now if the force is not in the same direction, for instance, I push on the chair here. I'm pushing downward, but the chair is moving that way. It's only the component of this force that's in the direction of motion. This component does no work on the chair at all, only the horizontal component. Okay? So there is a little computation in it, but if it's a constant force, it's easy to deal with. Now, before I go any further, let's see if I can get, is it aerial? Okay. All right. And baby, right? Okay. All right. That gets us up to 7. 3 to 7. Good. So, pretty easy definition for constant force. There are four fundamental types of forces. This sounds more like physics, doesn't it? Electromagnetic force, gravitational forces, electromagnetic forces, strong nuclear forces, and weak nuclear forces. Okay? I don't know why there's that in this context, but it's fine. Those are true. A force can be thought of as a push or a pull. That's the old physical science definition, before you get into anything else in physics. A force changes the state of rest or the state of motion of the body. Except for that boulder, I didn't change much at all. It did for a longest time. Okay. Like days, I was digging around that thing. Okay. Gravitational forces on the Earth. It is common to use units of measure corresponding to the weight of an object. I'm saying all this in a math book. All that's really very true. Okay? So here's example 1. Now maybe I'll see why they were saying all that, but let's see. Determine the work done by lifting a 50-pound object 4 feet. Any guesses? Say again? 200's a number. Okay? Say again? Foot-pounds. Very good. Okay? The unit for work. And by the way, the reason that's true, if you're lifting it, your force is upward. And of course, the 50 pounds is its weight, which is caused by the gravitational force, which is pulling downward. So your force is in the same direction of the displacement. Okay? So yeah, that's just simply 200 foot-pounds. Now, have any of you ever used a wrench that was calibrated in foot-pounds? No. Ever heard of a torque wrench? Okay? Okay, a torque wrench is calibrated in foot-pounds. Are you measuring work? No, you're measuring torque. Okay? And here's the difference. And you probably have gotten here, but if you haven't, you'll get there. This is either it may have been in your trig class. Okay? Did y'all do dot products or cross products of vectors? Okay, if you've done that, work is a dot product. Force dot displacement. Okay? When it's called force is a vector and displacement is a vector. That's a dot product. That's the end of the same direction as cosine. That's that. And a dot product produces a scalar answer. Even though you're multiplying two vectors, you get a scalar answer. Work and energy are scalar numbers, not vector numbers, not vector quantities. So this is that. Your torque wrench, on the other hand, your force is in this direction. The displacement is how long that was from here. And those are perpendicular to each other. That's a cross product. And the result there is also foot-pounds in the U.S. customary, but that's not measuring work, that's measuring torque. And torque is a vector quantity, not a scalar quantity, because that's the cross product, which produces a vector. So just in case you run into those units, don't think anytime you see foot-pounds it's going to be work or it's going to be torque. Both use the same units, but they're different quantities. So one's cross and one's a, and those are maximum for perpendicular force and displacement. Okay. Not part of the course at all. Okay? So I think that's all. They may go through a lot more mess to get there, but let's see how they do it. Oh, they draw a picture. I didn't do that. I did move my hands around. The magnitude required, the force to lift the weight of the object, that's what we're looking for, its magnitude, from the ground level to 4 feet high, 50 pounds, that's simply 200 foot-pounds. Okay. Force is in the same direction as the displacement, so it's just simple multiplication because it's a constant force. Okay? So the work done lifting at 4 feet, 50 pounds times 4 feet, 200 foot-pounds. All right. The U.S. measurement system, the work is typically expressed in foot-pounds. You could use inch-pounds if you're really talking very small things, or foot-tons if you're talking huge quantities, okay? In the international system, the SI, the basic unit of force, is the Newton, okay? And for force required to produce the acceleration of 1 meter per second on a mass of 1 kilogram, okay? In this system, work is typically expressed as Newton meters, as this is pound feet or force times displacement. This is a Newton meter, force times displacement. A Newton meter is a joule, okay? Named after James Prescott joule, who did a lot of the early work, mechanical equivalent of heat in joule, and then joule have 2, of course, named after Sir Isaac. Okay, but they don't capitalize the unit when you spell it out, but they do capitalize the abbreviation. So when you have foot-pounds, that's not named after any person, but a Newton would be a capital N, a joule would be a capital J. Okay. In another system, going back, rather SI, which is still metric, is when you're dealing with very small quantities, centimeter gram second, CGS system, whereas the SI is used to be called the MKS system, meter kilogram second, MKS. Now we just call it SI. This is the basic unit of force is the dyne, and the dyne times a centimeter would be a earth. Okay, there it is. Hopefully there we have it. Now, back when I was in college, long, many decades ago, this was the worst part of physics, having to go back and forth between all the different units, because we didn't even talk SI then. It was MKS or CGS. And when you get up to these levels, what you multiply by, and then the units and all the other things. And my older brother, when he came home from college, I guess I was probably doing it in high school, he came home, oh, here's the thing. His physics professor told us this. You're not going to need this, I don't think, in anything that you do, but if you ever did, if this is a centimeter, what is that? It's an earth. It's a dyne centimeter. Oh, okay. So an earth was a dyne centimeter. A dyne centimeter. Okay. I don't know why they're doing all this in the math book. Who cares? They don't even do this much in physics. Table summarizes these units of measure commonly used to express work done in several conversion factories. U.S. customary, which we used to call the British system, but technically the British don't use it anymore. They are SI. Well, I say that. Officially they're SI, but if you go to Britain, they do things a lot in miles and everything else, just like we do. But officially they're SI. Okay? The measure of work would be foot-pounds, measure of force would be pounds, measure of distance work. That's the standard. International, which is SI system, I wish I'd say it that way, that System International, named French, the joule, the Newton, and the meter, and the CGS would then just be the erg, dyne, and centimeter. Another way to remember just the term erg, work and energy use the same units. And ENERGY is the middle three letters in energy. So if you ever are prone to forget it, if you ever needed to know it, most of the time we ignore that now. Corbin, right? Okay. All right. Anyone else come in? Okay. All right. So I don't know why they give all these to you, but foot-pound is in the same order of magnitude as a joule, okay? It's a little bit bigger than a joule because it takes 1.355 blah, blah, joules to make 1 foot-pound. And then to get from joules to erg, or erg to joules, multiplied by 10 to the 7. And you get that if you think of all the things that are multiplied by that. You're going from an acceleration of meters per second squared to centimeters per second squared, so that's a factor of 10 to the second, and then grams and kilograms, that's another 3, that's 1,000, which is another, that gives you 10 to the 5th, is that right? And then you multiply it again by a meter, it seems like it's one off, but anyway, it's 10 to the second. And newtons and dynes is 10 to the 5th off, okay? And compared to a pound, see, a pound is much larger than a newton, okay? The newton's a fairly small unit of force. Pound is bigger, so the dyne is tiny, very tiny. Joules and ergs, 10 to the 7th here, foot-pounds here. This is just going to the reverse of this. These are going to the reciprocals of this. Okay. So, a pound is 4.4 or so newtons. Okay. Why in the world they have all that in the math book? But we get it. Okay. Now, work done by a variable force. So no longer can you just multiply force times displacement. You have to do incremental pieces of it because the force is changing. When variable force is applied to an object, calculus is needed to determine the work done because the force is varying. You have to account for that variation because the amount of force changes as the object changes its position. For instance, the force required to compress a spring increases as the spring is compressed. And you probably, if you think about this, yeah, it makes sense. Think of the coil spring in your vehicle, right? I think vehicles still have coil springs, right? Okay, you put a little weight on it, and it compresses a little bit. Put a much bigger weight, and it compresses more. So the amount of compression is proportional to the force, right? Now, those are pretty mighty springs too. So that is an example of a variable force. Okay? Consider an object that is moving along a straight line from x equal A to x equal B by a continuously varying force f of x. See, this force doesn't just depend, it's not just a constant, it varies with the displacement, x. Let delta be a partition, and this book uses this more than any other that I've taught from. Usually delta means change in, but they're using delta to represent a partition. Other books, capital P, maybe with a subscript on it, that divides the interval from A to B into n subintervals determined by A is equal to x of 0, and then there's a short way over from that is x of 1, and x of 2, then x of 3, all the way up to x of n, and that is your B. Then your delta x of n, see that's why use the same symbol for a difference and the same symbol for the partition, I don't know. But that would be any x of I minus the previous x of I minus 1, that's that delta x of I. For each I, choose some value c in between x of I minus 1 and x of I, such that the x of I minus 1 is less than the ci, and that's less than x of I. So there's something in between those two. Okay? Now, at that ci, the force is f of ci, obviously. Okay? This is your x value. Okay? Because f is continuous, you can approximate the work done moving on that little bitty I subinterval by saying, well, it's approximately equal to that f there. Not exact, but close. Okay? All right. This is it Brandon?
Yes.
Is that okay? All right. Has anyone else come in since we're all right? Okay. All right. So that little increment of work that it took to move it that distance x of I, if you take that small enough, you can count this as a constant. The force somewhere in that interval, and choose the place in the interval where it best approximates is a good average force for that interval. So the delta Wi is the alpha c sub I, which is in this interval delta x sub I. Okay? It's shown here. So I don't know how this shows. Somewhere in here is your c sub I. Okay? And the force that represents a good representation of the work done here, to use the constant force there, that's alpha of c sub I. So that the total work done moving from x equal A to x equal B is the summation of all those little incremental works, okay, as you go. Okay, so it's the summation of the delta Wi, which is the summation of alpha c sub I times the delta x sub I. Now, not too far of a stretch than to imagine the work done is approximately that, and this is equal to that, would be approximately equal to the summation from x equal A to x equal B of alpha of x dx. Now that's jumping the gun big time. Mathematicians want you to spend a lot more time, Patrick, right? Yeah. Okay. A lot more time fiddling with that, but that's what you're down to. Okay? And sure enough, that's what they do here. This approximation appears to become better and better and better as your delta, that partition, the length of that is going to 0 as the n is going to infinity. So the work done is the limit. As that goes to this, n is going to infinity, delta is going to 0. The summation of all those, then that becomes the integral from x equal A to x equal B at your entire interval, alpha of x dx. Okay? And if you think force times displacement. Same thing as before, only you're doing incremental displacements and evaluating the force equals one of those, in a sense. And then summing all those together, or integrating all of those. Okay? So it's the same formula, it's just it's not a constant anymore. So here's the definition of work done. And by the way, the book has a little blurb here. She would be a decent paper topic. I don't think I've ever heard of her before. Emily de Breteuil, something like that. Major work by her was the translation of Newton's natural philosophy into French. So all she did was translate. Her translation and commentary greatly contributed to the acceptance of Newtonian science in Europe. It's pretty interesting because usually the rest of Europe wanted to follow Leibniz, okay? And, well, of course, he didn't do the physics part of it, but Newton was such an obnoxious character sometimes. He didn't make friends easily, but she did such a good job in the translation, it sounds like, that they did accept his Principia, which turned out to be the Bible for the next several hundred years, you know, of mechanics. Never had seen or heard of her name before. So here's the definition of work done by variable force. If an object is moved along a straight line by continuously varying force, alpha of x. Now what does that mean? It is an alpha of x here for ways and then it jumps to here and then to here. That's not continuously varying. This is a smooth varying force. Okay? Then the work W done by such a force as the object is moved from A to B is given by this as your summation. Limit as that goes to 0. This is the integral. Use this. Okay? Integral from A to B of alpha of x dx. Okay? So if you could define that force as a continuous function, then you've got it. All you have to do is integrate it. Because it's force times displacement. Just done in an integral. Okay, more verbiage here. Okay? The following are 3 laws in physics which were developed first by Robert Hooke, the first one, Isaac Newton, the second one. And you'll notice these guys were close to being contemporaries. Hooke was only, 7 years older than Newton. Okay? And Hooke was well established in the Royal Academy. He was British also. Royal Academy of Science, I think it was called, in Britain. And here came this young whippersnapper into the picture, Isaac Newton, who blew them all away, including Hooke, okay? And Hooke didn't particularly appreciate it, especially when Newton blew some of his stuff away too. Not the stuff on work, Hooke's law, that was well established. Some of the other things, he fought Newton on, Newton fought, Newton was not the easiest guy to work with, okay? And Hooke must not have been either. So here's Hooke's law. The force F, and this is your spring that we just talked about, the force F required to compress or stretch a spring within its elastic limits, okay? You can't overstretch a spring. We usually say you sprung the spring or something like that. Is proportional to the distance d that the spring is compressed or stretched from the original length. So therefore, proportionality is F is equal to K times D. Okay? So D is a displacement. Usually horizontal, it can be vertical, so it can be Kx or Ky. Okay? Where the constant proportionality is called the spring constant, sometimes called Hooke's constant. Okay? Depends on the specific nature of the spring. Any of you ever played with a slinky? Slinky, the spring constant would be very, very low. Your coil spring on your car, enormous. Okay, so this cake can vary pretty dramatically on the type of spring, the type of material, all that kind of stuff. So there's one place that's a variable force. It's a linear variation. Okay. Newton's law of universal gravitation, on the other hand, is a force between two particles, M1 and M2, the mass of the particles, proportional to the product of the masses, inversely proportional to the square of the distance between them, the two particles. So that would be F is equal to, this is the universal gravitational constant. It's a very small number, 6.67 times 10 to the minus 11 meter. Okay, that's an interesting way to say it. Cubic meters per kilogram second squared. Okay, that's not quite true. Okay, yeah, no, that is right. Okay, Terrell is here. All right. Okay. These are in the most fundamental units. A lot of times, I think I've seen this done. G would be Newton meter squared per kilogram squared. That's the way I'm used to seeing it. Makes sense because we multiply this with kilogram, that cancels out. Meter, that cancels out, so it leaves you with newtons over here. So, but that is correct. If you spell them out, it's cubic meters per kilogram second squared. Okay. Where G is the gravitational constant, universal gravitational constant. On the Earth, okay? Different planets, different constants, okay? So, on the Earth is universal, okay? Maybe we should say earthly gravitational constant rather than universal gravitation. And then Coulomb's law. Remember them mentioning Coulomb, did they? Yep, Charles Coulomb, French physicist. He was born after Newton died, but he worked mostly in electricity. In fact, the unit for charge is the Coulomb. The force F between two charges, Q1 and Q2, in a vacuum is proportional to the product of the charges, inversely proportional to the distance between the two charges. Hey, that sounds pretty familiar. Gravitational constant force, what do we just call that? I think it was F also, right? Yeah. I would call that L sub G. This is L sub C for Coulomb constant. That's some proportionality constant. Okay. Q1, Q2 divided by D squared. Whereas gravity is G, M1, M2 divided by D squared. So very, very similar in form. Where Q1 and Q2 are given in electrostatic units, coulombs, okay, D is in centimeters. Oh, whoa, okay. So there, I'd never do that. I'd never do it in centimeters. I'd always do it in meters and have the force in meters. But this is using centimeters and dynes. Okay. I just never do that. But they do it. And then probably your K is going to change too. Because you use different units. Okay. Yeah, it says F will be in dynes for a value of K equal 1. Usually we don't specify what the thing is. So, anyway, that's just a bunch of stuff there. Now, we had already done example 1, or did we skip that? Yeah, we did it. That was, so here's example 2. A force of 30 newtons compresses a spring 3/10 of a meter from its natural length of 1.5 meters. It's a pretty long spring, okay? Find the work done when compressing the spring an additional 3/10 of a meter, okay? All right. The wording in that is a little strange. What do you reckon the first thing we got to do here? There's several things. You can approach it several ways. What would be your approach to that problem? Second?
Yes, set up the integral.
Okay, he's ready to go for the integral. And what would that integral be?
Could you just subtract the two forces and then multiply by the new distance?
Okay.
To find the work.
Okay, when you say two different forces, what do you mean?
Yeah, so find the first work, and then could you find the second one using that same force?
Okay, I think I understand what you're asking, but I'm not absolutely certain. Tell me what to write down.
Yeah, I'll just do it. You can do the integral.
Okay. All right. Now, we know this is, the force here is Hooke's law, right? Springs, Hooke's law, spring constants. And that is F is equal to Kx, right? They use S. It's okay if I use X. I'm just used to writing X rather than S. No. What did they use? D. They use D. Whatever you use, the variable there, okay? I don't want to use D. Any ideas why I don't want to use D? Yeah, and then it'll be DD. Okay, that sort of is bizarre for some reason. So I want to use X. Okay, y'all okay with it? Okay. First thing we got to do is figure out what in the world K is, and that's what that first thing tells us. That the force of 30 newtons is going to compress the spring 0.3 meters, and so therefore we are able to calculate what our K is. Okay? So what would K be in this case? Divide both sides by 0.3 meters. Okay? Oops. And what you have, everything goes out here. K is equal to, move that decimal one place, move this one place, and you get 3 in the 300 will be 100 Newton per meter. And that's the usual unit that we use for spring constant, force for distance. Okay. Now, the length of 1.5 meters. It says find the work done in compressing the spring an additional 0.3 meters. Okay. Now there's where the verbiage gets a little almost tricky, though it's okay. I think I'll just move this. I was going to erase more, but let me do this. Okay. So it sounds like to me you've already compressed the spring to 0.3 meters. So that's your starting point. And then you're going to compress it an additional. So that's going from 0.3 to 0.6. Now that's how I read it. Let me see and make sure that's what they're talking about. Yep, that's what they're doing. Okay? And by the way, the integral here is from A to B of f of x dx. Is that what they call it too? Yep, they call it delta x dx. Okay? So we've just gotten from here and there, your f of x is equal to 100x. Pretty simple formula. That's what it is. 100, that's your spring constant times x. So this will be 100x dx. And that's all there is to it. Well, a little bit more. Sort of be helpful to pull the 100 outside the integral. And what's the antiderivative? I'll write it down again. From 0.3 to 0.6 of x dx. Okay. Pretty hard calculus here, isn't it? What's your antiderivative of x dx? X squared over 2. Evaluated from 0.3 to 0.6. Now, the hard part here is, of course, the math, okay? First thing I'm going to do is do the 2 into 100 and make it 50, just to keep from messing with that. And then, what's this? 0.6 squared is, not that hard, 0.36 minus 0.3 squared is, second, 0.09, okay? So this will be 50 times 0.27, is it? Yeah. And that would be, second? 32.5?
Right, 13.5.
Yeah, 13.5, yeah. 13.5, okay? And the units would be joules, because it's Newton meters you're dealing with. So that would be joules. 13.5 joules. Okay? Is that what? Oh, good for them, they got it too. Now, of course, they probably did some of their maneuvering differently than me. I just found it easier to get rid of things early. Okay. Any questions? All right. The only thing that was, oh, and by the way, LarsonCalculus.com has an interactive version of this type of example. It may not be this exact example, or it may be, I don't know. But that's the procedure. The first line up there, basically you needed to calculate what your spring constant was, because you need to know what the force is. So then the spring constant, that goes into the force, and then you integrate from there. The second part, the part that was sort of confusing, is the work done compressing the spring an additional 3 meters. That meant you compressed it the first time to get the spring constant, but then you kept compressing it after that. You know, so fine. That was to me a little bit bizarre. All right, any questions on this before I erase it? Let's see how they did it. They may explain it a little better or differently or whatever. By Hooke's law, the force F of x requires to compress a spring x units, see they're using x here, from its natural length is F of x is equal to kx. Okay? Because F of 0.3 is 30, that's what the first thing said, the force necessary to compress it from its natural length, 0.3 of a meter, is 30 newtons. It follows that the K would then be 100. K would be 100 newtons per meter. Okay? So that's this being 30. Yeah, right here. They wrote it here, divide both sides with 0.3. And you get k is equal to 100. That now is what you use in your integral. And here's the picture they showed. Thank you for drawing that, so I didn't have to. There was this natural length when it's at rest, no force is on it. You compress it a little bit, 0.3 meters out of the natural length of 1.5 meters, so that's about a fifth of the way. You compress that, and you get that the spring constant is 100. Then from that you've already compress it another 3/10, so you're going from 3/10 to 6/10 is your change of x, using this expression there, alpha of x equals k, which is 100 times x. So that's your variable force here. Okay? To find the increment of work, if you want to do that, assume that the force is required to compress the spring over a small increment delta x is nearly constant, and that was our assumption from the beginning. So the incremental work is F times the distance increment. But the F is not just amount, it's a variable force of F, 100x times delta x. And because the spring is compressed from 0.3, where you stopped from finding the spring constant, an additional 3/10 to 0.6 meters is less than its natural length, you can do that. You couldn't compress it to 1.8. The spring is only 1.5. Probably couldn't even compress it all the way to 1.5. But certainly that's doable. Then your integral is from 0.3 to 0.6. That's your x limits from 100x dx. And they did the same thing I did. They took half of, I pulled the 100 out earlier, and then to pull out on 1/2 earlier, made it 50x squared, evaluated from 0.6 to 0.3. And I didn't do the math that way, but you certainly can. Now, let's go to example 2. Any questions on that? They got it done for 13.5 joules.
What was that? Just example 2.
What's that?
Is that example 1?
That was example 2. Oh, the next is also example. Oh, yeah, I'm sorry. Thought they were moving to the next one. Note that you did not integrate from 0 to 0.6 because you're not finding that. You've already compressed it, and then you're compressing it more. You're asked to determine the work done from compressing it an additional 0.3 meters, not including the first 0.3 meters. You could have also done the problem, how much work did you do to compress that 0.3 meters? Then you've been going from 0 to 0.3. That would have been a different answer because it is a variable force over that thing.
So could you technically do it like one integral from 0 to 6 to find the first, or one integral from 0 to 3 and the second one from 0 to 6?
And take a difference, yeah, exactly. Is that what you were saying earlier?
Yeah.
Okay, yeah, you could do that. I didn't understand what you were meaning by that. Okay, yeah, you certainly could. I thought you were saying from one measure to another. I just couldn't figure out which ones you were talking about. Yeah, you certainly could do that. That works. Because work is a scalar quantity, not vectors involved. So yeah, you could add, subtract, just like you do numbers. Okay. Now, trying to see where this slide comes into play here. Seems like it's stuff we've already talked about. I don't even see it on here. Oh, there it is. Okay. Okay. It's after example 3. So let's back up. Okay. And there's Justin. All right. Does anyone else come in since I called roll? All right. They don't have example 3 on the slides, so let's us do example 3. Moving a space object into orbit. A space module weighs 15 metric tons on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles above the Earth, as shown in figure 749? Okay? Oh man, do I want to draw that? I'd rather not. Okay? But not all of you have your books. Okay? This is going to be a really rough rendition of this. There's the Earth. Okay? The Earth has a radius of approximately 4,000 miles. That's an approximation, but we'll live with it. Okay? And you're going to project this module 800 miles from the surface of the Earth. Okay? To get it up there. Okay. Now, obviously, mine's not to scale, because 800 miles would be 1/5 of the 4,000, and I've got a lot bigger than that, but get over it. You know, just get the idea. Okay. This module weighs 15 metric tons. What is weight? It's a force. Okay? So that's the force you're dealing with. Okay? Now that's at the surface of the Earth. So F at 4,000, okay, is going to be, what did I say? 15 metric tons. Now, what's a metric ton? Does anyone know? It's a megagram. Okay? A kilogram, this book would be probably 1 to 2 kilograms. That's 1,000 grams. And 1,000 kilograms is a metric ton. And by the way, a kilogram, now that's a mass unit, okay? And on the surface of the Earth, mass and weight differ only by the acceleration due to gravity, which is an acceleration which has units in it. And that's, but we can compare those, or think of them in these terms anyway. A pound, a kilogram weighs about 2.2 pounds. That's the best way to say it. Kilogram is a mass, it weighs about 2.2 pounds. So if you had 1,000 kilograms, that would be how many pounds? 2,200 pounds. What's 2,000 pounds? A ton. So a metric ton is actually a little bit heavier than a U.S. customary ton, but a metric ton is a mass unit, not a weight unit. So you have to keep that in mind. So this 15 metric tons, that's a megagram, okay, which is a mass unit, okay? So, except they say weighs, okay, which is driving me nuts here because weight is a force. That's why this is a math book, not a physics book. They're using the terms really, really poorly there. So I've got to read on and see which one. How much work is done in propelling to a height of 800 miles above the Earth is shown in this figure? Use 4,000 miles as the radius of the Earth. Do not consider the effect of air resistance, which is a really big thing, or the weight of the propellant, which is another big issue, okay? Now, if you go back to Newton's law of gravitation, what you use is the center of the Earth, not the surface of the Earth, the center of the Earth, okay? because you assume that all the mass is located at one point. You remember free body diagrams, that type of thing, you assume everything is at that point. So you assume from the center of the Earth. So what you're doing is from 4,000 to 4,800. That's going to be your integral, okay, once we get to take an integral, okay. And there are just all sorts of things here. Here they have the module weighing metric tons, which weight is a force unit, whereas metric ton is a mass unit, okay, which is, why didn't they just say 15 tons? What do you get? I don't know. That would make this whole problem make more sense, okay? Because the weight of the body varies inversely as the square from the, what we have here is the force as a function of distance from the Earth is equal to, okay, this is Newton's, kind of like Newton's law of gravitation, okay, except rather than G and M and all those things, we're just going to put a constant C, okay, where C is the constant proportionality. Because the module weighs 15 metric tons on the surface of the Earth, the radius of the Earth is approximately 4,000 miles. You have, and they're sort of doing this like Hooke's constant. 15, and they're just going to call it metric tons and forget about units here. And they're going to square miles, which has nothing to do with feet. I mean, this is a really bizarre way. Physicists would be turning somersaults and Newton would be going crazy over this, okay? So what they're saying here is equal to C times x squared, where x is the 4,000 squared, okay? This is going to get you your constant proportionality. Well, 4,000 squared is 16 million, okay? Because you square the 4, but then you double your zeros, okay? So that's that. So then multiply 16 million by 15, and hopefully they've done it in the book for us, 240 million. So C is equal to 240 million. Nice, small, round number, right? Easily remembered. Not that you have to. Okay. Now, there's your constant. And then what we would do is integrate. Well, so this will be 240 million. I'm all in favor of scientific notation here, over x squared. So there's your variable force, and what you're integrating is from 4,000 to 4,800. And now your dx is in miles, by the way, which is really strange. And let's pull the 240. Let me put million. Okay, so I don't have to write all that out front here. 240 million times 1 over x dx, x squared dx. Okay? So your total force, or what do they call this? Work done, so work. Okay. So the total work done in this. Now, how do you integrate 1 over x squared? What's the best way to do it? Good approach to it. Yes, rewrite that as x to the minus 2. So let's do this integral. Can I just erase what I have in there and write in its place x to the minus 2? Okay. And how do we integrate this? So in front we have 240 million. Okay, I'll I'll do it that way, maybe make it a lot easier to see. What's the antiderivative of x to the minus 2? Negative 1 over x. That's okay. Negative x is x to the minus 1 over minus 1, so it's minus 1 over x minus 1, which is that exactly. And we're evaluating that from 4,000 to 4,800. Okay. Yeah. Okay. So that would be 240 million. Okay, I'm going to go back to my calculums, I think. Okay. And this will be minus 1 over 4,800 plus minus a minus, which is a plus, 1 over 4,000. Now, I could do that, least common denominator, all that stuff. You got calculators. Someone plug it in and see what you get. 1 over 4,000 is going to be a pretty small decimal number. Minus 1 over 4,800 is going to be a good smaller decimal number. The difference of those is going to be a pretty small decimal number. Multiply that by 240 million. And what do you get? Second? 10,000? Yep, 10,000. Okay. And the units are miles, tons. Now, if I read that mile ton, I would assume that's a 2,000 pound ton. I think that's what they meant. I really don't think they meant metric ton. I think they meant tons. And I can't rationalize why they did it. They're treating it as if it's a force. The metric ton is not a force, so I'm pretty sure. Just take out the term metric everywhere, and this problem makes sense now, okay? Because they don't say mile metric ton, they say mile tons. So, by all means, do that. Now, then they say in SI units, they tell you how many joules that is. Do y'all really want to do unit conversions in here? I mean, hopefully you know how to do those in physics classes and things like this. They just throw out the numbers and tell you what it is. There is, I think, a fairly easy way to do this, but that's not what this course is about. This is supposed to be calculus, so let's just let that ride. You can pick that up in physics. Okay, so that's your answer. Mile tons. Well, no, they do change it to foot pounds. So let me show you how to do that. I'm going to erase it all and start off with 10,000 mile tons, okay? My goodness, this is so bizarre. 10,000 mile tons, which is such a strange unit, but that, if you're truly talking tons, that is a work unit, okay? Metric tons, no, you have other things to do there, okay? So what you want to do is get this to, I think that'll do for it now. You want to get it to foot pounds. Okay? So I've put places for two conversion factors. Okay? You got to get mile tons to foot pounds. So you got to get miles to feet and tons to pounds. Okay? Now I put my conversion factors as 2 lines multiplied here. The first line is for numbers. Second line for units. Is this how you've done it? Or I'll just show you how. In both cases here. So I say always put the units in their place before you even mess with a number anywhere. So let's put the units into place. Which unit do you want to do first? Miles and feet or tons and pounds? I don't care. Miles and feet. So the second line is for this. Which goes where? Miles, feet, one goes on bottom, one goes on top. Miles where? Bottom, right. Okay. And feet on top. How many feet in a mile or how many miles in a foot?
Is it 1,600?
Second?
1,600 feet in miles?
No, you're thinking something else. It's 5,280 feet is 1 mile. Okay? 5,280 feet. This was easier for me to remember because of when I lived. Okay? Do y'all, and you probably don't remember this, back when U.S. and Britain and stuff, we used this for our races, okay? For instance, that track around the football field. Football fields are still measured in feet and yards, right? But I bet you the tracks these days are measured in meters.
Yeah, that's why I said 1,600.
Okay, I see what you're saying. It's a close approximation, but not quite the same. Okay? Now, the old tracks around the football fields were basically 440 yards. About 440 yards. That's a quarter of a mile. So knowing that, a quarter of a mile, if you think of it, 100 yards, actually 120 yards approximately, counting the end zones, and then you still had some room. So double that, and then the curve around here. Yeah, that's 440 yards. That was a quarter of a mile. 80 was half a mile, so that made a mile 16. Yeah, 16, 60. Right?
60,
Yeah. 1760. 1760. Multiply that by 3, 52.8. Okay? So, that's how many feet in a mile. Okay, so you got that conversion done. Now the second, put the units in their place. What unit goes where? Between pounds and tons. Tons on bottom. And pounds on top. And what's that conversion? How many pounds in a ton or tons in a pound? Say again? 2,000 pounds in a ton. Okay? Now, boy, this is going to be some big numbers here. And this gives you how many foot-pounds, and if you got a calculator, punch that in, and you find out that is an enormous number. I'll just use it in the book because I assume they're right. 1.164. Anyone get that? Just multiply the numerators, divide by the denominators. They're all 1, so don't mess with that. So 10,000 times 2,000 would be 20 million times 5,280. They say this is that time 10 to the 11th. Okay, I'll assume they're right. Foot-pounds. And then if you want to go back and get joules, use the conversion I gave you earlier. And the same way, same thing would happen there. Foot-pounds times blank. I mean, joules per foot-pound, they gave it to you earlier. Add your numbers with the units, you know. Like that. That, to me, is the easy way to do conversions. Now, this whole problem would have made a lot more sense if they hadn't said metric tons. If they had just said tons, this is perfect. This is perfectly right. So I'm pretty sure that term metric is wrong. Metric ton and English ton are close but not the same. If they had just left off the term metric, that just made the whole problem screwy. Okay. So that's done. Let's oh yeah, we can do that. Okay. Let me get caught up with where we are. That was here. Okay, we'll pick up here after break. Can't believe we... All right. Now, here's a summation of increments in this form. If you got your incremental work, that's your basically sort of an average force over that distance increment. The increments are pretty small, they're pretty close to being a constant. So it's delta x, okay? Another way to form that increment of work would be your little increment of work would be the force increment over a given distance, which is a weird way to say it. That second interpretation of delta W is useful in problems involving the movement of non-rigid substances such as fluids and chains. And in that case, it's your distance is fixed, it's the forces that vary in some senses, which is a kind of a weird way to express it, but I guess it worked. Okay? I think the next example is going to try to illustrate to us. Emptying a tank of oil. A spherical tank, let's see if they draw a picture for us. Yes, they do. Good for them. A spherical tank of radius 8 feet. Okay? Now, you don't see many spherical tanks, but I can think of one place. There's not oil that's in it. It's water. Anyone think of one? The big peach going down in Clinton. Okay? Spherical tank. Pretty close to it anyway. Okay, radius 8 feet, and what they have drawn here is your the XY axis. The X is at the bottom of the tank, which is a good place for it, and the Y axis is going right up the center of the tank, which is a good place for it. That means the 8-foot radius, these would be measured in feet, 0 to 8, 0 to 8, okay, to get the entire tank. Okay, so that's our setup and our scale. And of course then the top of the tank would be at 16 feet, okay, because then you have two radii together. So that would be the top of the tank is 16 feet. Now, bottom of the tank is 0 feet on the y-axis, okay. It's half full of oil that weighs 50 pounds per cubic foot. And that's okay. The way they've written it is fine. That is called a weight density, 50 pounds per cubic feet. I'd rather use that terminology, but it's correct. 50 pounds for each cubic foot. Find the work required to pump all the oil out of the hole in the top of the tank. So there's a hole at the top you see there. So you want to pump all of that out. Okay? Now, what your assumption here is, we're only doing we're doing delta Y's obviously, little segments of oil, strips of oil, what's the better word for it, cylinders of oil of varying radii, okay, these little cylinders, and you're going to have a delta Y, which ultimately is going to lead to dy, and if it's leading to dy, we know we're pumping oil out from 0 to 8, okay, or at least that's what it is. So that any strip here, delta Y, is going to define a little cylinder of oil, and the radius is a variable radius, so we're going to have to fiddle with that. But the radius is going to be on your x variable, okay? But we're doing dy, so we need to get that x in terms of y, okay? Now, how far are you pumping the oil, okay? Now, since you put your y equals 0 at the bottom, this strip is y units from the bottom, but you're pumping it out of a hole at the top, so how far are you pumping? 16 minus y. That was how high that little cylinder of oil is y, and so you're pumping this 16 minus y. So that's how much you're having width, okay? So that gives you your height of the pumping, okay, in terms of y. And what you have is your strip here with a radius of x. Well, you've got to get that x in terms of y. Okay? Now, so let's catch up where we are so far. Consider the oil to be subdivided into disks of thickness delta y of radius x, shown here. So the next task is to define that x in terms of y. Okay? Now, obviously when y is 0, x is 0, but you're right at the bottom then, so you don't know. And as you go up here, you're going up to a place where y is equal, x is equal to 8 when y is equal to 8. Okay? 0, 0 there. Okay? Almost sounds like it's linear. It's not. Okay? So what we have to do is draw. I don't see that they do this, but let's do this. Let's imagine that is your 8 there, to the edge. No, yeah, at the surface here. And the strip here, this is also 8, okay? What we want to get is this radius, which is here, okay? That's your x that's here, okay? Now, remember this is your y, so 8, this is 8 minus y here. This is a right angle here. This is 8. So your x is, and this is your x here. So we know that, let's try Pythagorean theorem here and do x squared plus 8 minus y squared is equal to 64. Would that be true? Okay, so we are going to solve for this. So let's say x squared is equal to 64 minus, let's go on and multiply that out. Well, that squared is going to be 64 minus 16y plus y squared, right? 64s are going to go out, and that leaves us x squared is equal to 16y, because of the minus and minus, minus y squared. Okay. Now, that's what x squared is. Can we get by with that? Yeah, because what we're looking for here is the volume of this, and the volume is the area of that disk, which is pi x squared, right, times delta y, right? Well, pi x squared would be pi times 16y minus y squared delta y. Okay, I think we found an easy way to do that. Now let me make sure. Well, they're doing a lot of other things too. But yeah, x squared plus 8 minus, well, they say y minus 8 squared. Doesn't matter which way you do it. Is equal to 8 squared. So yeah, we did the same thing. So I think that part works out well. Okay? Now, what that gives you is the volume of that disk. That's what this thing is. Okay? And that's in cubic feet, because your y is in cubic feet, your delta y is in cubic, everything's in cubic feet. Okay, and the 8 was in cubic feet, so, in feet. So the amount of oil in there, or the weight of oil, is the 50 pounds times the density, weight times the volume. This is the volume, and that will give you weight per unit volume times the volume gives you the weight, okay, or force. So that would be 50 pi. That's where they get the 50 pi, 16y minus y squared delta y. Okay. Now they do know that they do it exactly that way too. Okay. So this gives you your delta, oh, what are they calling this? I don't want to call it delta W. Is that what they call it? Yeah, they call it that too. The incremental weight for a disk of that size. Okay? And that's your force, and your force you're pumping, 16 minus y. We already determined that. So here is your force times your distance will then be the integral, the total work done, and this is a bit bizarre. I use little w for weight. They use it for capital W for work, which is a decent thing too. You just multiply your distance, which is this thing right here, by your weight. So their delta capital W is then 50 pi times 16y minus y squared times 16 minus y times delta y. Okay. And that will give you force times the displacement. Okay? Which is work. Okay. And that's what we're integrating. Now, the question is it easier? I think it is. Let's go and multiply these two out. Okay. What does that give you? Whoa, big numbers. 16 times 16 is 256. So the 50 pi is out front. Okay. And this will be 256y. Okay. Minus 16y squared. That's your outers. Minus 16y squared again, so that would be minus 32y squared. Okay, and then plus y cubed. And your delta y. Okay, so that's your delta W, the incremental work. So integrate that from 0 to 8. That gives you half a tank, 0 to 8. 50 pi put out front, no reason to drag that around in the integration. 256y minus 32y squared plus y cubed dy. Okay. It's alright if I erase some of this. There's just not enough room to write on the screen. So I'm going to erase this down here. I think we've already done all this work here. Okay. So the integral, the 50 pi is out front. Now you integrate the integration there. What would that give you? Anybody? Second? 128 y squared minus 32 y cubed over 3 plus y to the 4th over 4 evaluated from 0 to 8. Okay? Yeah. Alright. Now, the 0 part is easy. I'll do that part. Okay? So the other part is 50 pi. And you tell me what that is. Oh boy. Get a calculator. Okay? I don't want to do that in my head. 128 times 64. Someone do something. A little louder. 8,192
Yes.
minus, okay, 8 cubed, I don't know what it is. So 8 cubed times 32, take that number and divide by 3.
5,461.
61, okay, we'll round, okay, plus, and 8 to the 4th power, oh, wait, yeah, okay, divided by 4, that'll be a nice round number.
1,000.
Second?
1,024.
1,024. Okay. All right. So that would be 9,214 minus 5,461. You get some big old hairy numbers here. 3,754 times 50 pi, so multiply that by 50. That by 50 would be
187.
Second?
187,700.
2,700.
No, 700.
Second?
700.
700.
187,700.
700 pi. Or did you multiply by, you didn't multiply by pi already, did you? Or did you? Okay.
I just multiplied 50 by the 3.
Yeah, okay. So that's pi, and then you multiply that by the pi, and that's about 3. It looks like approximately the same number they get. 589,782 foot-pounds. Anyone get anywhere close to that? I've not got a calculator, so I don't know if this is accurate or not. 782 foot-pounds. Now, I'm a little hard-pressed to make sure that that is what we're dealing with. Yeah, we got pounds, we got feet. So, yeah, that looks pretty reasonable. Okay? And they estimate the weight of the oil is the volume of the oil in the hemisphere times 50, because that's the density of the oil. And if you lifted the entire half tank of oil 8 feet to get it to the top, that would be on the order of 429,000 foot-pounds. It seems like that's a reasonable answer. Okay? Now, it seemed like there was something I was going to say on that, but let's just let it go. All right. So any questions on that? Oh, I guess they're going to do it for us. So let's see how they do it. Because you have an incremental force acting on the disk by its weight, given by the weight, what I was calling delta W, little w, they're calling delta F, the weight. That's 50 pounds per cubic feet times the volume. And the volume was pi x squared delta y, and 50 times that, so that's where the 50 pi came from. For a circle of radius 8 and centered at 0, 8, you have the x squared plus y minus 8 squared, we did that, is equal to 64. So that came out x squared is equal to 16y minus y squared, exactly what we got. So putting that in for your x squared, you get the delta F, which is the incremental weight, 50 pi, well, they haven't done it yet, x squared delta y, and put in the x squared is 16y minus y squared delta y. You note that the disk, at y feet from the bottom, must be moved the distance of y minus 16 minus y feet. So that's your force times your displacement. And the force is the incremental part here. So that would have your delta y in it times that displacement. Same numbers we got. When you integrate that, pull the 50 pi out front, okay? And there they did. And 128y squared minus 32 thirds y cubed, right, all like that. And they came up with, we estimated at this point, and then filled in the others, they kept the thirds in there, okay, which is really a big pain in the neck. But then at this point, they do an estimate as well, which is about that. So I hope our estimate came out very close to theirs. We estimated early, and I don't think it'll make a lot of difference. Now here's what I was going to say. If this was a physics class, this makes almost, say, no sense. Having that many digits makes no sense, because in the original problem we were told 8 feet, 50 pounds. Basically, you don't have more than 1 or 2 significant digits anywhere. You can't get 6 significant digits out of that. So basically, about the best you can say is about 600,000 foot-pounds. So carrying all those digits doesn't make sense physically. But this is a math book. They don't worry about that. Okay. Now, let's see if they do the next example. This is going the same thing I read. I didn't know they were going to do this on the slide. To estimate the reasonableness of this, just imagine that you pick that half tank up and lift it at 8 feet in the air. There you've done basically the same thing, but that only counts that every piece of that is going up 8 feet. Well, in reality, the top layer is going up 8 feet, but then the other layers are going up more than 8 feet. At the very bottom, that last little disc there is going up 16 feet. So this will underestimate, but it still gives you a reasonably close answer, because your volume gets much less further down the bed. So you're off by a bit, but not too bad. And they don't do example 5 or 6. So let's try doing those if we have time to get them done. Okay. A 20-foot chain weighing 5 pounds per foot is lying coiled on the ground. How much work is required to raise one end of the chain to a height of 20 feet so that it is fully extended? Okay? Now they show the picture on the side, and they're using a front-end loader to lift the chain, which is fine with me. But you're lifting it, and they're saying how much work. Okay? So you're going from a situation of the chain all on the ground here to a situation where the chain is lifted straight up 20 feet. Okay? And the chain has a linear density of 5 pounds per foot. So, trying to remember what linear density is. Is that rho is equal to 5 pounds per foot? It really isn't, because that would be gram or kilograms per foot or per meter, but we'll just use that symbol. Okay? Now, obviously you're doing a dy again. Okay? So for each length that you lift, okay, well, you're not doing it by length, but you can almost think of that as your dy. So you're doing a dy here, and each of these dys you're lifting. Now the very top one you're lifting 20 feet, but the last one down here basically isn't getting lifted at all. So you've got a variable lift here. So every foot that you go up, you're doing, and your dy is measured in feet, the length that you lift, let's call this length that you lifted here y, and the y is going from 0 to 20. So you got part of your integral already figured out. 0 to 20, okay, and you're going a dy. Okay. Now, 5 pounds per length, that would then be, and you're lifting dy, so the weight, little w, they call it F sub w or something else, that would be 5 dy. Okay? That's how much weight you're lifting every little increment that you lift. 5 dy. Okay? They call it delta F, I'm calling it delta little w for weight. Okay? They put weight in parentheses. Now, the weight you're lifting a distance, and how far are you lifting it? Any point here, you're a distance y. So that then is just that's the weight times the distance, so your incremental work, okay, would be 5y dy. Now I'm saying dy, they're probably calling, no, they're saying dy, so that, or they're saying delta y so far. Okay, now you're ranging that from 0 to 20, so I mean we're basically set up here. 5y dy. That's it. Okay, I thought it was going to be a lot more involved in this, but it isn't. What's the integral there? Antiderivative? Oh, we can pull the 5 on the outside. Let's do that. And what's the antiderivative of y dy? Pretty easy. Antiderivative of y dy. Y squared over 2. Okay? Evaluate that from 0 to 20. And that would give us 5 times 20 squared is 400 over 2. 0 squared is nothing. 2 will go into 400, 200. And this would be 1,000. Whoa. Yep. We're in feet, foot-pounds, I guess it is. Okay. 1,000 foot-pounds. Very good. Now, in the next example, so let me erase that. That was a pretty straightforward and relatively simple one. So let's do the next one, which probably won't be. Okay. And we don't have the figure, and I sure hate to try to draw this one. You'll consider the piston of radius little r in a cylinder casing. As the gas in the cylinder expands, in other words, you've fired it off, you know, with your spark plug, or you, if it's a diesel engine, it's spontaneously combusted. So as the gas in the cylinder expands, the piston moves, the work is done. So P is the pressure in the gas. Okay? And that's in pounds per square feet, by the way. P pounds per square feet. Okay? Now, a lot of times we say pounds per square inch is the pressure, PSI. That is a legitimate pressure. They're using pounds per square feet, which should be an enormously large number. Okay? So pounds per square inch is usually pretty good size, but if you're doing per square foot, that's a lot of force in a square foot. Okay. Against the piston head, which is in square feet, which is rather strange, I would say square inches, but they're going to use square feet. And V is the volume of the gas in cubic feet. So V is the volume of gas in cubic feet. Okay? Yeah. Then the work increment involved in moving the piston delta X feet I guess you need the picture of the piston. If this is your cylinder, okay, supposedly a right circular cylinder, and here's your piston somewhere in there, okay, that's pushed back this way. The radius here is little r. So the area here of the piston head is pi little r squared. Okay? The distance here that it's been pushed back is your x, and you're measuring the incremental dx's. Okay? So that's what we're living with. So, the work done, the delta W, incremental work, moving that incremental dx there, force times the distance. Well, force is pounds per square feet times square feet, and the square feet would be your radius there, so that would be your pressure times pi r squared, where r is the radius of that cylinder, in feet, which is really bizarre to have that big a number. Pounds per square inch seems like it would make much more sense here. Okay? Your delta x here is how much the volume is changing. So your delta v is pi r squared, that's your radius, dr. I'm sorry, dx. Pi r squared dx. Pi r squared is the area of that cylinder and piston, and the dx is how far it moves, so that's going to be your volume. And so your incremental volume would be that dx. So the pressure, let's see, so to get the r squared out of the pictures here, what you have is this is your incremental work. Well, it's not incremental because you don't have your V here. That's multiplied by dx. Okay. I forgot to put that. Okay. And the volume is this first part right here. This part is the volume, so your pressure times the change of volume, that is the amount of work. Okay? That gets the R's out of the picture. You don't need to know what size piston that is. So that gets you down to work this. You integrate both sides of this. The work then is that pressure, which seems like to me, I don't guess that's you're assuming it's not it doesn't change with displacement, which I guess is an okay thing to do. And the pi can come out. No, I'm sorry. Well, they just leave dV, okay? They don't do anything with it. Assuming the pressure of the gas is inversely proportional to its volume, you have that P is equal to K over V, where K is your proportionality constant, and the integral then is this. So the pressure is K over V. Okay. Now, why is that okay to do? Okay? Well, is it Boyle's law that product of pressure times volume is a constant? Okay, that is Boyle's law. Okay, I think so. So that's where that comes from. So then you can do, now you got it in terms of V. So your integral here then becomes, because this does depend on volume, that's where the problem was. So you have the integral, pull the pi, let's see, forget about pi, okay? So this would be that the constant, that can go on the outside, times dV over V, okay? Now, what is that going to wind up being? Antiderivative of 1 over V dV. Anyone remember that one? Second? It's what? No? Okay. If you're thinking V to the minus 1 dV, and you're trying to use the power law, for this, that would be V to the 0 over 0. Problems there, folks. Can't do that. So what's 1 over V dV? Very special little function. Second? No, not E, the ln. You got it. That's the log of V. So it's K times the log of V. So that's what we're getting at in between your V's. So example 6 then is using that. A quantity of gas with an initial volume of 1 cubic feet and a pressure of 500 pounds per square foot expands to a volume of 2 cubic feet. Find the work done by the gas. Assume the pressure is inversely proportional to the volume. Okay? So I'm going to need to erase parts of this, but I don't know which parts yet, so let me just do this. The pressure in this, well, let's see. I'm going to keep my pen a little bit longer, and then I'll erase some. So your volume is going from 1 to 2 cubic feet. I think it is, right? Yeah. Okay. Find the work done by the gas. Assume the pressure is inversely proportional to the volume. So your pressure is K over V. Okay. Like we said before, so we'll take that out. Okay. I think I can take my ugly picture out. I hope I won't need it anymore. basically to show the other. I don't need that anymore, I don't think. We will need that, but not this part. I'm not even sure about this, so I'll take that out too. Okay, let's see what we got now. The pressure is 500 pounds. Okay, now find the work done by the gas as you expand from 1 cubic feet to 2 cubic feet. Okay? What we had before, and I'm afraid I erased it. No, I got it still there. So we do know at the beginning, that's where the 500 is, that the 500 is equal to K over 1 cubic foot. So the K is equal to 500 when you multiply K times V, this is pound per square foot, and this is cubic feet. When you multiply those together, this comes out to be a measure in feet. Now, I don't know if that, they don't say that, but it does have that unit. So the work done by the gas is, this delta W is the K, which is 500 feet, okay, times the integral from 1 to 2 of dV over V, okay, which is 500 feet times, and what's the antiderivative of 1 over V? You said it before? Okay, the log of V evaluated from 1 to 2, which is 500 feet okay, times the log of 2. I left off minus the log of 1. Why is that legal? At 0. Okay. So I think that comes out. Now the problem is the units are a bit messy. I probably couldn't carry it around, but the total work is in foot-pounds. And if you do that, log 2 times 500, hopefully you'll get something close to 347. Do you? 500 times the log of 2. ln of 2. Okay, about 347 foot-pounds. Which means that log 2 is measured in pounds, and I, for the life of me, would not be hard-pressed to describe how that's true. So we'll just take the word for it. Okay, that finishes 7.5 finally. Okay, and homework exercises here. Do either 5 or 7. They're both at Calc Chat. 7's at Calc View. Do any of the odds for Hooke's Law 9 through, goodness gracious, 9 through 13. They're all at Calc Chat. 11's at Calc View. Then do any of the odds that you're interested in. 15 or 17 or propulsion, so I'll do at least one of those. 19 and 21 are both pumping water. Actually, 23 is 2, 25 is 2. 27 is pumping gasoline, which is almost the same. So I would say do at least one, and more if you would like, of the odds 19 through 27. I'd say through 25 and then do 27. That's sort of a separate They're all at CapChat. Winding the chain, do either 29 or 31. Both are at CapChat, 29 is at CapView. Lifting the chain, that's at 33. And exploring concepts, 35. You can think about those if you would like. Newton's law of universal gravitation is 37. Electric force is 39. Boyle's law is 43. Hydraulic press, do either 45 or 47 or both. And then you can look at 49 if you're interested. Goodness gracious. All right. Any questions? 7.5. Okay. Now, that's all for 7.5. Now, what I'm going to do next, and I may live to regret it, is just do a slideshow on 7.6. In case any of you do run into this, you need it. Hopefully, you will have seen it, understood it enough that you can follow on through this. It sounded like most of you probably won't need this, but just by chance that you would. And it starts off with a bunch of stuff that generally math texts usually don't have this kind of stuff in it, but this one seems to do. I guess he's a very practical seeming guy. These are moments, centers of mass, and centroids. First is to understand the definition of center of mass. We're not going to do all these, but anyway, this is what we're moving towards. So let's look first at mass. And this is mostly physics stuff, so I'm not going to go into this too much. Newton's second law, fundamental equation, force equal mass times acceleration. We won't go into that, but it's an important thing to know. This table, I can't believe they have it. Most physics books don't list this, but we never measure mass, I won't say never, hardly ever in the U.S. customary system. What's the unit for it? Mass. We never use it. It's a slug. How many times have you gone to the grocery store and said, I'd like 3 slugs of lettuce, please? You know, not going to happen, okay? No one uses mass slug. It doesn't even have an abbreviation. Notice when you use it, you have to spell it out and abbreviate everything else, okay? No one uses it. International kilogram, CGS is gram. Frankly, this book is on CGS. Most people don't use CGS anymore. The force would then be a pound. That's what we use in U.S. customary. We never measure mass. And SI is kilogram for mass, Newton for forces or weights, and CGS is grams of dynes. No one uses that. And they give the conversions here. I can't believe they do this, but they do. Some of these are really far-fetched conversions. Like 1 dyne is 0.0000224. You really don't need these. You can look them up if you ever need it. And we're not going to go into this, and this is just using your definitions and stuff. So I'll show it to you, but you can figure it out on your own. No one ever measures slugs, so why mess with it? Okay? Oh, there is something else said. Because many applications involving mass occur on the Earth's surface, this amount of mass is referred to as a pound mass. So if they ever use it, they're going to use that term rather than slug. Okay? Center of mass of a one-dimensional system. Okay, now this is where things start getting more more engineering type, and physics too. Okay? The moment about a point is defined to be the mass of the point, of the thing at that point, times its distance from wherever your reference is, from that point, okay? X is called the length of the moment arm. That's very much an engineering type term, moment arm, okay? You'll probably run into this in statics and dynamics. So that's what we define as moment. You have a point, say, here's your origin. You have a mass sitting out here. This moment is mass times the distance between the origin, wherever you're dealing with, okay? Now, the concept of moment can be demonstrated simply by a seesaw. I can remember when I was young, I was usually the heaviest one in my class, and I always had to sit way short on the seesaw, and everybody else was far back. So I always had to do it. I had more work to do to keep them moving, okay? A child with 20 kilograms sits 2 meters to the left of the fulcrum. Older child with 30 kilograms sits 2 meters to the right. It's going to go down and not move unless you push it up. So what you have to do is move the fulcrum to get them to balance out. Get the moments to be the same. Okay? So that just shows. And by the way, the moments are measured in mass, length measured, kilogram meters. I don't think anyone measures these in slug feet. They're probably going to say that later. No one does. Kilogram meters, that makes sense. Okay? So, what if you put several things on either side of a fulcrum? The fulcrum is the center of this, and this is sort of a lever system. So let's say we had a bunch of masses here, M1, and it's x1 units from the center, so that is moment. M2 is x2 from the center, so that would be its moment. And M3 would be over here. That's going to be a negative number there, M3 times x3. M sub n minus 1 times x sub n minus 1, and M sub n times x sub n. So here you have your formula for whatever system you have here. If that's in equilibrium, then those moments all add to 0. Okay? And that's usually what we want to happen. That would be statics. It's all equal to 0. Nothing's moving. You're in equilibrium. Okay. The moment about the origin denoted by M sub 0 can be written as M sub 0, moment about the origin, M1, x1 plus M2, x2, but all the way up. That thing we just had. If that moment about the origin is 0, then you're in equilibrium, you're in a static state. Okay? For a system that is not in equilibrium, the center of mass is defined to be the point x bar at which the fulcrum could be relocated to obtain an equilibrium. That system were translated to x bar units, then each coordinate x of I would be x of I minus x bar. You're doing how far from that center of mass you are. So then you have the summation of all your masses times how far you are from the center of mass, and do these up. Well, summations follow the same rules as integral. Summation of a difference is the difference of the summation. So the summation of I equal 1 to n of mi xi is all the moments, okay, minus the moment of the center of mass, and that would be at 0. So what you have then, your x bar would be the summation of your moments divided by the total mass. If you take out the x bar, which is just a constant, then this is the summation of all your masses. This is when you're in equilibrium, that's your center of mass. That's how you can locate the center of mass, at least in the x coordinate. Okay? And we are doing one-dimensional only right here. So there's a definition for your center of mass. Summation of your moments about the origin divided by the summation of your masses in that. So this is saying the same thing. Let the point masses be M1, M2 through Mn, located at these positions x1, x2, xn. Then the moment about the origin would be M sub O, think of that as the origin, okay? Or the 0, whichever you want it to be. and that would be M1x1 plus M2x plus all those. Take that moment, sum of all those, and divide it by the mass. There's your location of your center of mass. Okay? Because this is a product of mass times distance, so this would be kilogram meter, kilogram meter, kilogram meter, distance kilogram meter divided by kilograms. That gives you the location of your center of mass in the x direction. Now, this would be a problem here. We could probably do this almost in our head. This would have a moment of minus 50, right? They don't even give units, so we'll just leave the units off. Minus 50, what's the moment here? 0, because it's sitting on 0, okay? So this, I'm assuming these are masses, okay? This would be plus 20, so minus 50 plus 20, and there's a plus 70. So that's plus 40, right? So plus 40 is your, say, kilogram meters, whatever units you have here, plus 40. Divide by the total mass. Now you have to include that mass. You don't exclude that because it has a mass. So that's 15, 20, 5, 35, 40. So divide, what did I say it was? How quickly I forget. 90 minus 50, 40. 40 divided by 40, it would be at 1. That should be the center of mass. If I did it right, okay. Yep, x bar is at 1. The point masses will be in equilibrium if you located the fulcrum there. Now, this is just an arbitrary scale you start with, but it's what you measure from. If you move the fulcrum right there, not there, but here, then that would be perfectly balanced. Okay? You could go back and calculate then. If your fulcrum is here, that's 15 times 1 is 15, and this would be 60, so that would be 75 on this side. Over here, you would be 3 times 5 is 15, and 10 times 6 would be 60. That's 75 plus. So yeah, that would be perfectly balanced. M equal 1. Okay. Now, rather than defining a moment of mass, you could define the moment of a force. In this context, the center of mass would be called the center of gravity. Rather than center of mass, center of gravity if you're talking about weights there. So that's fine to do too. And your forces are mass times accelerations. Newton's law, okay, second law. So that would be your total force from all those masses if they're all moving at the same acceleration. Okay. Now, torque. We talked about it before. That is your sort of a twisting force type thing. That's your moment times your displacement. Okay? Well, actually, force times the displacement, because M1A is a so that's a force times the displacement, and if you divide that by the force, then you have the center of gravity, not center of mass, center of gravity. That would be the same. And they're saying that the center of gravity and the center of mass would have the same location. Well, that's just because your mass, everything's multiplied by a constant. So if you divide out the constant, you got the same thing. Not going over great detail here, probably more than I need. Center of mass in a two-dimensional system. Okay. Now we have locations x1, y1, x2, y3, x3, y3, all the way up to x sub n and y sub n. And rather than finding a single moment with respect to the origin, you have two moments. one with respect to the x-axis and one with respect to the y-axis. Now here's the part that gets, you have to sort of keep it straight in your head. The moment with respect to the x-axis, with respect to the y-axis, is your mass times your x displacement, because this is the y-axis. So that would be m2 x2 plus m n xn plus m1 x1. You know, that's your moment with respect to the y-axis. To the x-axis is your mass times respect times the distance from the y-axis. From the x-axis, which is the moment with respect to y. So just remember, in a two-dimensional system, there's a moment about the x-axis, a y-axis we call m sub y, moment about the x-axis m sub x. But this is the product of your mass times your x displacement. That's the distance from the y-axis, and this is the moment m sub x would be distance from the y-axis. So it seems a little backward, but if you think about it, it's got to be that. Okay? So here are your definitions then. Two-dimensional system, if you have n masses there, okay, at all these different locations, the moment about the y-axis, m sub y, is m1 x1. So again, about the y-axis, you have your multiplier by this, because this is how far you are from your y-axis. M1 x1 is m2, all like this. About the x-axis is the m1 y1. Add those together. The center of mass, your x bar, is your x bar is your m sub y divided by m, because that's where your x's are, x bar, and your y bar are your moments with respect to the x-axis, which are the products of your m's with your y's divided by m. That gives you your y bar. So frankly, I just as soon forget about calling these moments and just think of this as sum of the mx's, divide that by the sum of m's, that gives you your x bar. Throwing in the m sub y there just seems to be a complicating issue, except in engineering you refer to it that way, so you have to do it. And where your m is the sum of all your masses. So these, what we were calling before, just moment, this is moment from the y-axis, that gives you your x bar, and the moment from the x-axis, that gives you your y bar. Okay. Moment of a system of masses in a plane can be taken in any horizontal or vertical line. In general, the moment about a line is the sum of the product of the masses and the directed distances from that. This is really getting a little further bizarre. If you got a horizontal line, y is equal to b, and you're taking the moment with respect to that line b, then that would be m1 y1 minus b, because this is y is equal to b. And so the distance you are from that line b and each mass. And if a vertical line x equal a, you do it this way. Rather than the x and y axis, you do it some vertical line and horizontal line other than that. So I think this one we'll probably be able to do in our heads, but we might. Let's just see. Center of mass, system of point masses, and these are where they're located. Well, let's not worry with it. Those are the masses, and they give relative sizes by the size of the circles there. The smallest mass is M3, the biggest mass is M1. No, M4. And you would do that moment for each one of them. You do the masses, the moments. Remember, a moment about the y-axis is the mass times the x value. So do that, and then your center of mass is the moment about y, which is your x values. So they would give you your center of mass for the system. Okay. Those are individual masses. Guess what? Most of the time we don't have individual masses. But it's helpful to understand that. Most of the time you have some blob out there. That blob could be a planar blob called a lamina. It could be a volume blob, volumetric blob. So you have to do your calculations from that. So what we'll do here is a thin, flat plane of material of constant density. You can't get more uniform than that, okay? A planar lamina. The density is a measure of mass per unit volume, such as grams per cubic centimeter and blah, blah, whatever. For planar laminas, the density is considered to be mass per unit area because you're only dealing with the plane, okay? So the density is denoted by rho, lowercase Greek letter rho. And most of the time in physics, they have different ones. Lambda is for linear density. S, I think, is for area density, like we're talking about here. And rho would actually only be volume density. This book uses rho for any of them. So you have to pay attention to that. And basically, your center of mass would be where you could balance it. If you knew that center of mass, where it would be. If this is constant density, it's in the geometric center. Okay? So that's what makes masses planar lamina. If they're constant density, then you don't have to worry about anything else. Now, this is what you run into where your problems come. Considered an irregularly shaped planar lamina of uniform density rho. So the density is constant now. Bounded by two graphs. Y is equal to f of x on top, and y is equal to g of x on the bottom. So the mass of this region would be its density, which is rho, constant, times the area. So the first thing you've got to do is get the area here. Well, the obvious way to do the areas here is dx here, and then f minus g, both functions of x, so that's a function of x, times your dx, integrate that from a to b. Densities are pretty, mass, total mass is pretty easy to get. The constant density times the integral f of x minus g of x. Just like we did back, when was it? Last chapter or somewhere there. And that gave us your area there times the density, and this is a density per unit area. That would give you your total mass. Okay? That's pretty straightforward. Did the easy part first. Okay? To find the center of mass, you then have to partition the interval into n subintervals, and again, use your delta x's because delta y's would really be difficult to deal with. So let x of I be the center of the ith subinterval, okay, and approximate the portion of the lamina line, blah, blah. So the height there is f of x of I minus g of x of I, just like we did before. The density of the rectangle, rho times the volume. The volume would be the height times the width. So doesn't look a whole lot different from what we did before. Okay? That's, again, mass. Okay? Now considering that mass to be located the center there of the rectangle, the directed distance from the x-axis to that would be the average distance from of that. So it would be, add these up, divide by 2. That's going to be the center of mass from the from the x-axis. So the moment about the x-axis, m's of x, is going to be that y value, m times y, which is density rho times this times that. That's your mass, and then your distance is the average distance between these two y's, f and g. So it's that. So all this is a function of x, which you can integrate. Okay? So they showed you that part. That's the more difficult part. The m sub y is just x times the distance there. Okay? X is how far you are from it, and that's the length, that's the width, there's the mass, that's your mass times the distance. So this one's an easy one to do on that. This one's a little more complicated because you don't have the x there, you have this as the distance. Okay? This times that, that's your mass. So if you ever need to do these are the type formulas you'll run into. And let's see how much more there is. Not going to do the examples.
It's fun stuff.
Yeah. Is it?
Oh no, I said it's fun stuff.
What's that?
I said fun stuff.
I still
like it. It's fun. Like, I was sarcasm.
Okay.
No, sorry.
Sorry, my ears not good. Okay. Let's see where we are in the text. I think this may be enough. Let's just see where we are now. I think we're in that part. Example 4. Okay. Theorem of Pappus is just sort of a strange little thing. I don't know if you'll need this or run into it, but basically what it says, if you've got a region of space that you're rotating around an interval, then the volume is the area times 2 pi times that radius, which is hopefully what you would expect it to be. But you can solve all sorts of fairly complicated problems this way. A torus denotes the area. The area is pi r squared. And then pi r squared times 2 pi r, and you'll get exactly what your the volume of that torus would be, which would be a pain in the neck to do any other way. Okay? And they show you an example of that. And that's it. So, we'll start next time, and no homework exercises there, 7.7. Okay, so maybe it's good I didn't have the test ready today. You could have gotten started on the first part, but the last section we wouldn't have had yet. I know this was exciting. Have a good weekend. All right, take care.